Welcome to Blockchain, the animated course. I'm Blocky, your host. This is Unit 1, the fundamentals of blockchain. Here's everything we'll cover, in order, consensus with a real-world analogy and a worked example for every single topic. Let's go. Unit 1, Topic 1, Origin of Blockchain. A ledger is simply the record of who owns what and who paid whom. For 5,000 years, every ledger shared one weakness. Someone keeps the book. You must trust that someone not to lose it, fake it, or lock you out of it. 1982, cryptographer David Chaum proposes eCash, coins made of math that can't be forged, the first serious digital money. But eCash still routed everything through one company's server. When DigiCash went bankrupt, the whole system vanished. Lesson: remove the middleman, or inherit his fragility. 1991, researchers Stuart Haber and Scott Stornetta invent linked timestamping, the direct ancestor of blockchain. Each document gets a cryptographic fingerprint, a hash. Think of a tamper-evident lab notebook, numbered pages, ink, a notary stamping every page's date. The trick: every new stamp includes the previous stamp's fingerprint. Backdate or alter any document and every later link visibly breaks. A chain of proof. They even printed their running hash in the New York Times classifieds every week, making the whole newspaper reading world their notary. You can't bribe every reader. 1992, Merkle trees join the design, letting one link seal thousands of records at once. We'll build one, hash by hash, later in this video. Through the 90s and 2000s, Hashcash contributes proof of work. B-Money and BitGold sketch community-run money. Every ingredient of blockchain now exists, but nobody has combined them. 2008, the global financial crisis. Banks collapse, governments bail them out, and trust in financial middlemen craters. On October 31, 2008, a person or group under the name Satoshi Nakamoto publishes a 9-page white paper combining all the ingredients, chained hashes plus Merkle trees plus proof of work. The result: digital cash with no central company to trust, and no central company to fail. Chaum's dream without Chaum's weakness. January 3, 2009, Satoshi mines block number 0, the Genesis block, the first block ever, the anchor every later blockchains back to. Inside it, Satoshi embedded that day's real London Times headline. Why? A headline can't be known in advance, so the block provably wasn't created before January 3, 2009. It's also a timestamp, a witness, and a manifesto in one line. 2010, the first real-world purchase, 10,000 Bitcoin for 2 pizzas. 2015, Ethereum makes the ledger programmable. Unit 2, then enterprise private chains arrive. Unit 4. Blockchain grew from digital cash into something more general, a machine that lets strangers agree on shared records without trusting any single keeper. Unit 1, Topic 2, the blockchain solution. A digital coin is just a file, and a file's superpower is also its curse. It can be copied perfectly, for free. So Alice copy-pastes her $10 to Bob and to Charlie. Both think they were paid. This is the double spend problem, the reason digital cash failed for 30 years. The classic fix: put a trusted bookkeeper in the middle. The bank keeps the one ledger and checks every payment against it. No double spend possible. But the middleman has a price. He can fail. He charges rent. He can exclude you, and you can't audit him. Trust becomes a bottleneck and a vulnerability. Blockchain's answer: don't replace the bookkeeper, multiply him. Imagine a village where every family keeps an identical copy of the notebook. When Alice pays Bob a goat, she announces it in the village square. Everyone writes it down. Everyone's copy agrees. To cheat, Alice would have to sneak into most houses and alter every copy, and the pages are glued in order. So a swapped page is instantly obvious. Cheating one book is easy, cheating the whole village is not. 4 terms you now own. Distributed ledger. Trustless, immutable, transparent. Next, watch a real payment travel through this system, step by step. This mesh is the peer-to-peer network. Every dot is a node, a computer holding its own full copy of the ledger. No server, no center. Step 1. Create and sign. Alice builds a transaction, from, to, amount. Then she signs it with her private key, a signature only she can produce, but anyone can verify. Step 2. Broadcast. She hands it to the nearest node, and nodes gossip it onward until the whole network has seen it. Step 3. Validate. Every node independently checks. Real signature, sufficient balance in history not spent already? No node trusts another node's word for it. Watch Alice try the old trick. A second transaction sending the same 5 coins to Charlie, at the same moment. Node C2 transactions spending 1 balance. Only one can make it into a block. The other is rejected network-wide. Double spend. Solved. Step 4. Block. A miner, or validator, gathers valid pending transactions and packs them into a candidate block. Step 5. Consensus. The network agrees this block is the next page of the ledger. How they agree, proof of work, proof of stake, is this video's final chapter. Step 6. Append. The block is chained to the previous one and every node updates its copy. Bob is paid, with no bank, no clearinghouse. Number 3-day settlement. The scoreboard. Blockchain doesn't remove trust, it relocates it, from one institution's promise to math, replication, and majority consensus. Unit 1. Topic 3. Components of blockchain. Analogy for this whole chapter. Blockchain is a global postal and notary system. Each component maps to a piece of that system. Let's meet all 10. Node. Any computer running the blockchain software. Like a post office in the network. A full node stores the entire ledger history. A light node stores just enough to verify what concerns it. Ledger. The shared record itself. Replicated on every full node. It is append only. New pages can be added at the end, but old pages are never edited or torn out. Transaction. The smallest unit of work. One signed instruction to move value or data. The letters flowing through our postal system. Keys. Every user holds a key pair. The private key is a secret seal ring only you possess. The public key is your visible address anyone can check the seal against. Alice signs the message "Pay Bob 5" with her private key. The output is a digital signature, a wax seal computed from both the key and the exact message. Any node runs verify, with her public key. True. It proves who sent it. Only Alice's key makes this seal. And that nothing was altered. Change 5 to 500 and the same signature fails instantly. Authentication plus integrity. No notary office required. Hash function. The fingerprint machine. Feed it anything. It returns a fixed length fingerprint. These are real SHA-256 values. Check them yourself. One capital letter changed, hello to hello, and the entire fingerprint is different. That's the avalanche effect. The smallest tamper screams. Deterministic, fixed size, one way, collision resistant. This is the tamper alarm the entire chain is built from. Remember it for the block anatomy chapter. Nonce, number used once. A counter inside each block that miners crank like a dial to change the block's hash. Why they crank it? The mining chapter at the end of this video. Block. The mailbag. A batch of validated transactions plus a header that seals and chains it. Full anatomy in the next chapter. Consensus mechanism. The postmaster's daily meeting. The rule by which thousands of strangers agree on the one next page of the ledger. Proof of work. Proof of stake. Final chapter. Wallet. Software that guards your key pair. Common exam trap. Coins never sit inside a wallet. Balances live on the ledger. The wallet holds the keys that can move them. Lose the keys, lose the coins, forever. Peer-to-peer network, no headquarters, nodes gossip, each tells its neighbors, who tell theirs, until everyone knows. Kill any node and the gossip simply roots around it. 10 components, 1 machine. Users sign transactions with their keys. Nodes gossip them over the peer-to-peer network. Miners pack them into blocks using hashes and a nonce. Consensus appends them to every copy of the ledger, and wallets hold the keys that make it personal. Unit 1. Topic 4. Block in a blockchain. Zoom into one block. Every block has 2 parts, a header, the seal and label of the mailbag, and a body, the actual cargo of transactions. The body, a list of validated transactions. Real blocks pack in thousands. We'll use 4 so we can follow every hash by hand. The header holds 6 fields. 2 do the heavy lifting, the previous block hash, which chains this block to the last one, and the Merkle root, one fingerprint that seals every transaction in the body. And the block's own identity? Hash the header. That fingerprint is what the next block stores as its previous hash, block by block, fingerprint by fingerprint, a chain. Analogy, a family tree of receipts. Each receipt gets a fingerprint. Pairs of fingerprints are combined and refingerprinted. Parents, grandparents, until one ancestor fingerprint represents them all. Level 1. Hash each transaction. These are real truncated SHA-256 values of the texts below. H1, H2, H3, H4. Level 2. Pair them up and hash the pairs. H12 seals transactions 1 and 2. H34 seals 3 and 4. The parents of our receipt family tree. Level 3. Hash the 2 parents together. The Merkle root. 1/8 billion times compressed fingerprint of every transaction below. This is the value stored in the block header. Bonus. To prove TX3 is in the block you only need H4, H12 and the root. 3 hashes, not 4 transactions. For 1 million transactions, only about 20 hashes. That's why phone wallets can verify payments without storing the whole chain. Now let's attack it. An insider edits TX3. Dan pays Eve 7 becomes Dan pays Eve 700. 1-digit pair. Watch the tree. H3 recomputes to a completely different value. Avalanche effect. The receipt's own fingerprint no longer matches. The corruption climbs the family tree. H34 changes. So the Merkle root changes, and it no longer matches the root sealed in the block header. Tamper detected. Zoom out. Each block's header stores the previous block's hash. Our attacker changed block number 101's contents, so block number 101's own fingerprint changed. Block number 102's stored prev hash now points at a fingerprint that no longer exists, so number 102 is invalid, which invalidates number 103, and so on to the tip. 1 edited digit, a broken chain. To succeed, the attacker must remine number 101 and every block after it. On the majority of the network's computers, faster than honest nodes extend the chain. That combined impossibility is what immutable actually means, not magic, just brutal economics. Follow any chain backwards and every prev hash path ends at one anchor. Block number 0, the Genesis block from January 3, 2009 we met in the origin story. Unit 1, Topic 5. The technology and the future. Blockchain isn't one invention, it's a stack, a gossip network at the bottom, cryptography above it, consensus above that, the chained ledger, and finally the applications you actually touch. Bitcoin lives only in that top layer. It's one dish cooked on this stove, not the stove. Swap the top layer and the same stack runs supply chains, land registries, or hospital records. In 1995, email was the internet's killer app, and skeptics concluded the internet was email. Then came the web, streaming, and app stores. Bitcoin is blockchain's email, the first killer app of a deeper technology, the web era of blockchain, programmable money, digital ownership, is what the rest of this course is about. 6 directions the stack is growing: self-executing contracts, bank-free finance, tokenized real-world assets, state-issued digital cash, identity you own, and machine-to-machine payments. 1 concrete future: a house sale, identity check, escrow, deed transfer and registry update, all 4 steps as one atomic chain of on-chain events, settled in minutes. The same transaction today, about 60 days, 5 paid intermediaries, and paperwork that can be lost or forged. That gap is the business case. Unit 5 walks each industry. Fair warning: many blockchain projects fail. Scalability, energy, regulation and integration costs are real. We'll treat them with full rigor in the final unit. Hype is not a consensus mechanism. Unit 1. Topic 6. Decentralization and Distribution. Analogy: cooking for a festival. 1 giant kitchen? Several neighborhood kitchens? Or a potluck where everyone cooks and everyone takes home the full menu? Those are our 3 network shapes. Shape 1. Centralized. Every participant connects to one hub. Efficient, simple, and the hub is a single point of failure and a single point of control. Shape 2. Decentralized. Several hubs share the load. No single boss, but small groups can still fail or collude. Shape 3. Distributed. A mesh. Every node connects to several others and holds a full copy of the data. This is the blockchain shape. The distinction exams love. Distribution asks where the data lives. Many machines. Decentralization asks WHO controls it. No single authority. They are independent properties. A bank running 3 mirror data centers is distributed but centralized. Many machines. One owner. Bitcoin is both. Many machines. No owner. Drill 1. Kill the bank's central server. Every branch, every card, every customer, offline instantly. 1 failure. Total outage. Drill 2. Attack the blockchain mesh. Let's knock out 4 of these 12 nodes. A brutal 33% failure, at random. Transactions reroute through surviving peers. And the key point: every survivor still holds the complete ledger. Nothing is lost. The network degrades gracefully instead of dying. Control is a slider, not a switch. Real systems sit anywhere between one boss and no boss, and that slider position is exactly what defines the types of blockchain. Up next. Unit 1. Topic 7. Types of blockchain. Public blockchain. The public park. Anyone can walk in, read every record, send transactions, even help validate. Bitcoin and Ethereum, also called permissionless. Private blockchain. The company office. One organization issues the badges. Who may read, who may write. Fast and controlled. The subject of Unit 4. Permissioned. Consortium. Federated blockchain. The boardroom. 5 rival shippers. 1 shared ledger. Jointly governed. No member owns it. All pre-selected members validate. Hybrid blockchain. The bank branch. A public lobby. Verifiable proofs. Public audits attached to a private vault. Sensitive data. Restricted rights. Reading rights. On a public chain every balance and contract is world readable. Private and consortium chains keep reads inside the membership. Writing rights. Public chains accept transactions from anyone with a key. Permissioned chains check your badge first. Validation. Public chains use open contests. Proof of work or stake. Permissioned chains appoint known validators. Proof of authority or PBFT voting. Unit 4. Speed. Fewer known validators means seconds fast finality. Open consensus across thousands of strangers is slower by design. Trust. Public equals trust nobody in particular. Private equals trust the owning organization. Consortium equals trust the member group. Names to remember: Bitcoin and Ethereum, Hyperledger Fabric and Corda, R3 and Energy Web, DragonChain and XinFin. Needs. Anyone can join. No authority can block users. Global reach. Openness beats speed. That's the public column. Verdict. Build on Ethereum. Needs. Strict privacy. One accountable owner. High speed. Known participants. That's the private column. Verdict. Hyperledger fabric. Run by the hospital group itself. Needs. Shared rights. Mutual distrust between a known set of firms. Joint governance. No single owner allowed. That's the consortium column. Verdict. A federated chain, all 5 validate. One question remains. The biggest one. However open or closed the door is, the people inside must agree on one shared history. Enter. Consensus. Unit 1. Topic 8. Consensus protocols. Before the algorithms, the ancient version of the problem, 4 generals surround a city. Attack together, they win. Attack separately, they die. They can only coordinate by messenger, and messengers get captured, and a traitor general may send attack to some and retreat to others. How do the loyal generals still agree? That's exactly a blockchain situation. Thousands of strangers' computers must agree on one history, while some may lie. The full siege, with the solution, is Unit 4. Today, the big consensus families. Family 1. Proof of work. Bitcoin's engine. Winning the right to write the next page costs real computational sweat, but verifying the winner takes anyone a millisecond. Worked example. Let's actually mine this block. Rule of the contest. Keep rehashing the header while cranking the nonce until the hash starts with 4 zeros. These are real SHA-256 values. After 35,597 guesses, nonce 35,597 produces a hash starting 0000. Puzzle solved. The miner broadcasts the block. Every node checks it with 1 hash and accepts. Solving. Hours of hardware. Checking. Instant. Each extra required 0 multiplies the guessing work 16-fold. That's difficulty. Bitcoin retunes it every 2016 blocks, so one block keeps taking about 10 minutes no matter how much hardware joins. Proof of work's honest weakness. With over half the total hash power, an attacker can rewrite recent blocks. Security isn't magic, it's economics. The attack costs more than it could ever earn. And proof of work's famous bill. The contest burns electricity on a national scale, which raises the question, can we get the same security without the sweat? Family 2. Proof of stake. Instead of burning electricity, validators lock up their own coins as collateral. A stake. Money at risk replaces work performed. Worked example. 4 validators stake 32, 100, 50 and 18 coins. 200 total. The protocol picks the next block proposer by stake-weighted lottery. Selection odds equals stake percent total. A 16%, B 50%, C 25%, D 9%. More collateral at risk, more chances to propose, and more to lose by cheating. Round 1. Validator B is selected, and proposes a block containing a fake payment. The other validators check it, and refuse to attest. The protocol slashes B's deposit. 100 coins burn down to 50, and B is ejected. Cheating doesn't just fail, it automatically costs half your capital. Honesty is simply the profitable strategy. This isn't theory. Ethereum, the number 2 blockchain, switched from work to stake in September 2022. The merge, cutting its energy use by roughly 99.9%. Delegated proof of stake. Democracy on chain. Holders elect a small parliament of block producers, blazing fast, but only as decentralized as 21 seats can be. Proof of authority. Forget anonymous contests. A handful of known, licensed validators sign blocks with their reputations. Perfect where members are already vetted. Private chains. PBFT. The direct, mathematical answer to the Byzantine generals. Members vote in structured rounds and agreement is guaranteed as long as fewer than 1/3 are traitors. Unit 4 dedicates a full chapter to it. Proof of elapsed time. Every node draws a lottery ticket, a random sleep, inside tamper-proof chip hardware. Shortest NAP proposes the block. Elegant, nearly free, if you trust Intel. The whole family on one card. Read it column-wise for the exam. Energy, only proof of work burns. Speed, permissioned wins. And who validates? Open contest versus known identities. The grand pattern. Public chains buy trust with work or stake. Expensive but open to strangers. Permissioned chains buy speed with known identities. Cheap, fast, but members only. Consensus chosen equals chain type chosen. That's Unit 1, complete. You now know where blockchain came from, the problem it solves, every component of the system, what lives inside a block, where the technology is heading, the difference between decentralization and distribution, the 4 types of blockchain, and the whole consensus family, from proof of work to proof of elapsed time. Next time, Unit 2, Ethereum, smart contracts, and your first lines of Solidity. See you there.